Hey everyone, welcome back. Today's going to be a fairly short video. It's going to be an introduction to conservation laws, and we're just going to spend a few minutes and do a worked example of just one of them. So there are three conservation laws that we're going to talk about: linear momentum, angular momentum, and then energy. Each of these three, in order for you to apply the conservation of linear momentum, conservation of energy, each of these three, they have very specific conditions that must be met in order for you to justify the application of these. So again, we're just going to talk about linear momentum today. Let's talk about the conditions where you can justify using it, and then what it means and how you put it into practice. The first conservation law, conservation of linear momentum. Let's go back to Newton's second law. We know that sum of forces is equal to ddt of linear momentum. Okay. Now, we actually applied this when we did the rocket science equation. We said, what happens if the left-hand side is equal to 0? So, what if sum of forces equals 0? Well, if sum of forces equals 0, okay, then the left-hand side is equal to 0, right? Then ddt of k has to equal 0. If ddt of k is equal to 0, that means that there's no change in k, right? This is the derivative of k with respect to time. So at time 0, you have a certain amount of momentum. At time 1, you have a certain amount of momentum. At time 2, you have a certain amount of momentum. So that's like saying k1 and k2 and k3. And every time you sample, you calculate the linear momentum of the system. And you will find that these are all equal to each other. And they're all equal, again, because there's no forces. If there's no forces, then there's no change in momentum. When we did the rocket equation, we did this on a system level, right? We included the ejected fuel, the ablated fuel, with the rocket itself. We can take this same claim, we can apply it to any system, as long as you can prove that there are no forces acting on it. So, how broadly applicable is this conservation law? What situations have the sum of forces equal to 0? Honestly, not many. It's frictionless situations, vacuum, non-deformable bodies. You have to make, honestly, a lot of assumptions in order to be able to apply this with any level of accuracy. There are some problems in your homework where you have to apply conservation of linear momentum. So let's do a quick example so that when you see those problems, you'll know what you're doing. The problem we're going to do is a collision problem. Let's take two bodies. I'm going to call this one body A, and I'm going to call this one body B. Here is body A, body B. Let's treat these like particles. Let's not worry about the rotation. And let's say that these two particles are zipping through space. They have some trajectories. And at some moment in the future, these things are going to collide. There's going to be a collision event. Here's some collision event. And then out of this collision event come the two particles again. So here is A and here is B. We're not going to apply conservation of linear momentum to the collision itself. We're actually going to talk about how to analyze collisions using impulse momentum theory, but that's going to be kind of close to the end of the semester. So for now, don't worry about the collision event itself. We're going to say that the sum of forces on the system is equal to 0. And that includes for the collision event. So whatever forces A is exerting on B, B also exerts those same forces on A, such that the sum of forces for the whole system is 0. This also means that there is no drag, there is no gravity, there are no external forces. So sum of forces on this system is equal to 0. If you can write this claim, if you can say that the sum of forces is equal to 0, then you can apply conservation of linear momentum. So let's say that over here on the left, these are the initial conditions. This is time number 1. There is some moment in the middle where there's a collision, and then over on the right we have time number 2. Okay, the claim that we're going to make using conservation of linear momentum is that k of the system at time 1 is equal to k of the system at time 2. Now, what's the usefulness of this? We've done something like this before, right? This helped us derive some rocket equations. This time, what we want to do is we want to use this equation to try to calculate or determine some information about the system at this second moment in time. So let's write out this momentum equation in greater detail. So k of the system time 1 equal to k of the system at time 2. There were 2 bodies, A and B. Each of them have they would have their own generalized coordinates. They would have their own trajectory. We would say that the mass of A times the velocity of A, you don't have to get any more specific than this for this, this derivation. It's the mass of A multiplied by the velocity of A. Again, we know that this is a vector. This is the velocity A at time number 1. We're not doing any ablation or accretion in this problem, so the mass itself is not changing with time. We're holding these constant, so it's just the linear momentum of body A at time 1 and the linear momentum of body B at time 1. So here's k of the system at time 1. We set this equal to k of the system at time 2. MAVA T2 plus MB VB at time 2. All right. This right here, this is literally conservation of linear momentum. This is all of the information that you can write down. Now, this equation is scalar. This equation is vector. The dimensions of this equation are 3 by 1. The masses are all scalar, but each one of these velocities are 3 by 1 vectors. So you could have potentially 3 equations here, right? You could separate each of these into the x, y, and z directions. Now, for the problem that we just drew, we drew it planar, which means you're already dropping it down to just x and y coordinates. Next thing I want you to consider is if you have one equation, you can solve it for one unknown. If you have 2 equations, 2 unknowns, 3 equations, 3 unknowns. So at most, how many equations can we, or how many unknowns can we solve for here? Well, if it was fully populated in 3D, we could solve for 3 unknowns. If we're doing a planar problem, we would solve for 2 unknowns, something like that. Where would those unknowns fit into the problem? What if I'm going to highlight some things. What kind of information do we already know? Well, maybe we know the masses. And if I know mass A and mass B, okay, that takes care of all these. Maybe I know their initial speeds. What if I know their velocity trajectories at time 1? Okay, that takes care of this. We go to this side. Can I solve for both VA and VB? No. Consider that this, if I don't know VA, that's 3 unknowns. If I don't know VB, that's 3 unknowns, right? So if I don't know VA and VB at time 2, there's 6 unknowns. And I only have 3 equations. At most, I only have 3 equations, right? So in order to actually use this conservation of linear momentum, to use only this, it requires that you have a whole bunch of information about the system, and let's pretend that we also know the velocity of A after the collision. So we knew exactly everything going in, and we know the velocity of A coming out, and now the only thing that we're missing is the velocity of B. You can use this equation to solve for the velocity of B. The problem that's in the homework, I don't remember if it asks you to solve for the velocity or maybe one of the unknown masses, something like that. But when you're looking at that problem, understand it's having you solve for just one unknown. And you can only solve for one unknown because you'll only have one equation in that problem. I think it's 2 balls bouncing in a line. Now, what if you didn't have information about this? What if you didn't know VA or VB? Well, then you can't use conservation of linear momentum to solve. Or at least you can't use only conservation of linear momentum to solve it. Consider that I had two other conservation laws. We could couple this with one of the other conservation laws, energy, for example, to write another expression and perhaps use that to solve. For now, though, this is it for conservation of linear momentum. It's not overly fancy. It's only applicable in very certain problems. So write this down and then go take a look at that homework problem. If you have concerns on it, let me know. That's it for this. Let's break. I'll see you next time. Stay safe.